So for this talk, I need you guys to take a sip of Red Bull if you got it, sip of coffee if you got it, take a deep breath, get prepared. I'm going to try to channel STL because, believe it or not, there's 196 slides in this presentation and a demo, and I've got 20 minutes. Okay, so since I'm going to try to channel STL here, let's see if I can. Didn't get this. I'll do this by hand. This is not good. Okay, so that is my talk on random. So, right there. That's one of my favorite Dilbert comics of all time. Now, my talk. Recap from my prior talk. Everybody here saw it, hopefully. But a quick recap. At the end, I said no raw pointers. Indirection through pointers changes semantics of copy, assignment, and equality. Creates incidental data structures. Thread safety concerns. It's inefficient. Shared pointers are as good as the global variables. That's from the prior talk to refresh your memory. But there's another deep problem. Inheritance is intrusive. What do I mean by that? There's no such thing as a polymorphic type. Okay? What we mean by polymorphism is we have a set of common requirements on using types, and we want to write a piece of code in terms of those common requirements and use it across types that happen to satisfy it. Okay? So a type is not polymorphic. We use a bunch of types in a polymorphic setting. So, by using inheritance to capture polymorphism, we shift the burden of use to the type implementation. We tightly couple our system together. Okay? Inheritance implies variable size. That implies heap allocation. The heap allocation forces a further burden to manage the object lifetimes. We get indirection. That's inefficient. We have to manage those object lifetimes. It encourages shared ownership, proliferation of these incidental data structures. Shared ownership leads to synchronization issues. It breaks our ability to do local reasoning and further impacts performance. And hence the title of this talk, Inheritance is the Base Class of Evil. So let's walk through what I had in the prior presentation, but we're going to take a little bit of a different take on it than before. So this is the same code we had before. We've got our document that consists of a vector of objects. Our objects are just integers. And we can draw our integers, our objects, and we can draw our document. Okay? But let's make it a little more complex and just wrap that integer into an object. Okay? All we did is we put a wrapper around it. We're going to let the compiler supply our copy and assignment operators because the default ones are just fine. This is the same code we had before with integers. Okay? And the same code works. We didn't change the semantics of the code. We just put a wrapper around. Okay. Now, let's make it a little bit more complex here. Let's add a level of indirection inside the object. Now we're actually going to go ahead and heap allocate our int. Hopefully you never actually do this in practice. But we're going to heap allocate our int. Okay? So now we've got a problem here with copy. Okay? So we're going to have to write a copy constructor. Okay? The semantics of copy, it's important in order to create a new object. We don't want intersecting objects here. And we're going to write an assignment operator. Okay? I like this form of an assignment operator, which is to copy and move or copy and swap if you were on C++ 98. This guarantees you a strong exception guarantee, which means that if I throw in the middle of the copy, my object's left unchanged. So, assignment, we want it to be consistent with our semantics for copy. Right? Now that we have that, we have this exact same code, and we get exactly the same output. Okay? So, we've just gone one level deeper in wrapping things up. So, One way to think about this is a private implementation or pointer to implementation idiom, handle body idiom. Okay, let's take a look here, though, at what goes on by decorating our class a little bit to see when we're doing construction and when we're doing copy. So quiz, see how awake you guys are. What will this print? Okay, we're going to put out CTOR or copy. Anybody got a guess? CTOR. Yep, even under C++ 98. Okay, why? Well, we got RVO. So the copy's alighted. But what's this going to print? Anybody?
Copy assign.
Copy assign. Well, we didn't decorate our assignment, but CTOR copy. Okay? So the copy is the copy we wrote inside of our assignment operator, right there. Okay? So the compiler can't alight it. We said make a copy. Okay? So now we're going to pull in a little bit of C++ 11. Okay? We're going to add a move CTOR, just the default move CTOR. Okay? And now we're going to rewrite our copy, or I'm sorry, we're going to add a move assignment operator, and we're going to rewrite our copy assignment operator just slightly, just so I can copy and paste this one all over my code, right? Which is to say now my assignment operator is in terms of make a copy and then do a move. Okay? So now what does this print? You guys know? STL should know. Well, there's no assign, but CTOR. Okay? It's just construction. No copy. What does this print? Okay? What I did is I reserved 5 elements. That's so that we don't get noise from growing our vector. Okay? And then I'm going to call an algorithm down there to reverse, which is going to swap things around in the vector. Okay? So, are we going to get copies? Anybody? Copies? No copies? People are thinking, yeah, we get a lot of copies here. Okay. Now, if you were in C++ 98, you would fix this by calling swap. Okay, providing the swap. But we can fix it here by adding a move constructor just equal to the default. Okay. std reverse is a permutation. It's going to be written in terms of move. In this case, it's going to be just swapping pairs of elements, and swap is written in terms of move. Okay? So we've got our default move constructor. Same code. All the copies go away. Okay? So this is getting pretty nice. And you see 3, 2, 1, 0. It did the reverse. Okay. So let's take that out for a minute. Now, you heard me say this before. In order to really utilize this move, we just want a general rule that we're going to be passing sync arguments by value. Okay, that's going to give the compiler an opportunity to decide whether or not it needs to make a copy based on whether or not the thing is an R value, okay, or whether or not it's an L value. And if it's an R value, it can either alight the copy altogether, or it can do a move. Okay. So we're going to take here, even though it's just an int, and we're just going to apply our own rule, and we're going to say pass the int by value and move it into place. It's a little silly with an int, but we're just going to be consistent with our code. Okay, but now we're going to make our class a little bit polymorphic, just a little bit. So we're going to add a way to construct our object from a string. Okay, and we're going to add a little string model down here, just like our int model. Okay. So we can't hold now, though, a pointer to an int model. So what are we going to hold a pointer to? We'll hold a pointer to our concept type. And we need to write that. So we're going to write a little concept type, which just has a virtualized destructor here to start. And we're going to inherit from it from those two models. We're going to add a draw method, virtualize that. Okay, we'll go back up here. We'll add a way that we can draw our strings. And right here, we're saying new int model. Okay, we don't want to do that anymore. What are we going to do? We're going to say, when we do a copy, we need to virtualize our copy. So we need to call through there. Which means we've got to come down here and add a copy function to our concept, add a copy to our string model, add a copy to our int model. Okay. Now from our client side, we've got a document that can hold integers or strings, and it prints that. People following so far? Everybody? Okay. So the point here is to not allow the polymorphism to interfere with the client code. It's all packaged up inside of our class. Polymorphism is just an implementation detail. But we got a bunch of redundant code here, right? This code's almost identical. Okay? We've got two draw functions here. Do we have a mechanism in the language to avoid this kind of copy and paste replication? Templates, yeah. Okay, so let's replace that with a template. Okay, now we got a templated constructor for our draw function. Okay, but now what are we making here? We got to make a new model of T. Okay, so down here, right, we've got two models. These are almost identical. So we're just going to replace those with a template that's a model of T. Okay. Now if you're on the client side, you can write your own class and provide a draw function for it. Okay? And insert that class into your document. Okay. And you get this output: 0, hello, 2, my class type, end of document. Okay? My class didn't have to inherit from anything. 0 and 1 and 2 did not have to inherit from anything. My string class is just an std string. It didn't have to inherit from anything. And yet I can use these all in a polymorphic setting. Okay? So the client isn't burdened with the polymorphism. Now here's an interesting thing. My document is drawable. Right? Just like 2 lines down there, I draw my document. So my document satisfies being drawable. So I can put a document into a document. Okay? Now, how many people think that this is going to be an infinitely recursive little thing if I put a document into itself? Anybody? Does everybody understand why it's not infinitely recursive?
Because you're copying.
Because I'm copying. Because it's all value semantics. Okay? So that's going to put out, I've got a document that contains 0, contains hello, which contains a document containing 0, containing hello. End of that first document. My class T in the outer document. That's what that's going to draw. Is that pretty cool? Okay. So, by shifting polymorphism from the type use, it allows for greater reuse and fewer dependencies in our code. We're using regular semantics for all the common basis operation, copy, assignment, and move helps to reduce our shared objects. We have regular types to promote interoperability, and there's no performance penalty in doing this. Okay? In fact, oftentimes it's faster because we don't have to pay for heap allocations when we don't need the polymorphism. Now I'm going to give you a really quick demo of a feature in an app I worked on once upon a time. And is there... Let me see here. There. Okay. So this is a picture. It's a little cropped off on the edges. I don't know if it's cropped off up there too, but hopefully you can see a little bit of the palette over on the right. Up until Photoshop 5, Photoshop had undo, but it only had single level undo. Okay? And if, I don't want that. Let me find our paintbrush here. Okay. And here I am adding paint strokes, just horrible stuff to my document, obliterating it here. And we had this problem when we were working on Photoshop 5 that Photoshop was written in terms of this command model from Mac App where every command had a bunch of methods on it that said do it, redo it, undo it, commit it. How many are familiar with similar patterns in application frameworks? Quite a few people. And we wanted to do multiple undo, so it seemed natural to just keep a list or a vector of these command objects. But the problem is when you did a do it, in order to do an undo it, it had to store away the data in there, and everything in Photoshop was a bunch of ref-counted pointers to everything else. And so when you did that, now you had pointers that might actually be aliasing to something else in the document. Okay? And so the subsequent command could screw up an undo buffer for a prior command. So it didn't quite work, and there's even in that time frame for Photoshop, there were hundreds, if not 1,000 commands in Photoshop, and it was a very difficult problem to try to go in and take this apart. So Mark Hamburg had this really brilliant idea. He said, oh, let's screw it. Let's get rid of these command objects with the do it, undo it, redo it, commit, and let's just have do it, and before we do it, we'll just make a copy of the document. I'm like, you're nuts. Photoshop documents are huge, right? These could be a gigapixel scan of Mars with 5 layers from JPL. Okay? But that's what Photoshop does. It just peels off copies of the document. And what you see over here on this side is my history stack, okay, which this is just a vector of my documents, and I can flip through them to do undo. Okay? So I can even go back a little bit, do a different stroke here, and now I still have all those stages. Okay? So, and once we did this, we said, this is kind of cool, because if we have the other document and we have things like a clone tool inside of Photoshop, then I could pick any state back here, okay, and let me erase something here, or do a different color so we can see this. And I have to go faster. Okay, so I could pick a state back here, and I could click on this little thing, and that's essentially setting my clone tool, and then I can pick my history brush, and I can go to a different point in time, and I can at a pixel level undo. Okay, so I can do pixel by pixel undo. Okay, and there's even this really cute thing called the art history brush. So I could do like a really kind of, hipster style artistic undo, pulling up pixels from the past. Okay. Okay, so you get way more stuff than just undo. So what does that have to do with this? Well, the way we pulled this off is we said we're just going to make copies of the document, but they're actually going to share stuff that's not modified. Okay? So making a copy of the document is instant. And we do this all the way down to the level if you change the caption of your photo, we peel off an entire copy of that document and change the caption. So let's write it. Okay? We want a history state, so we'll just do a vector of our documents. We're going to add 2 commands, commit and undo. Okay? Commit just does a pushback. Undo does a pop back. And we have the current state of our document. Okay? Just to see what's going on here, we're going to add a copy up there. Okay? And we're going to come down here, and we're going to change this a bit by saying, let's create a history. Let's take our current document, put 0 and hello, draw that, draw a line, commit it, add to our document, putting current my world, change an item number 1, which was hello, to world, draw that, put out a line, undo it, and draw it. Okay? And this is what we're getting. We got our document 0 hello. Bunch of copies, right? Copy, copy, copy. Then 0 world, because we changed hello to world. 0 hello, my class, 0 hello, right? That's the undo state going back to the first state at the bottom there. So everything worked, but we had a bunch of copies. Okay, that could be really expensive if you had if this were of huge documents and not a bunch of ints and strings. So, let's get rid of the copies. Let's just delete them. Done. No copy, no assignment. Get rid of our virtual copy. Gone. And we'll change this to say let's have a shared pointer to a concept, but to a const concept. Okay? So now a shared pointer to an immutable type has value semantics. Okay? Just to be optimal here, we're going to change this to just use make shared, avoid an extra heap allocation. Same code here. There we go. Everything works. So, compared to an inheritance space design, it's more flexible, it's non-intrusive, it's more efficient, it's less error prone, it's thread safe. And in less than 2 slides here, we created a polymorphic drawable object that can hold anything that implements a draw function, okay, and an undo stack that supports multiple undo, all in a page and a half of code. There you go. So I think I've got 1 minute, 33 seconds left here, if the clock is right. So that was blazing through. Question over here.
Yeah, the copy, you got rid of the copy functions.
Yes.
But, so how, if you made a change to it, I can see that it could be changed and undone. It was actually making a copy. It was actually making a copy via the const reference. Is that what was going? Because I'm not sure where the other copy was.
Okay, so I think what he's referring to is when we change the string hello to world, but it was const inside. How did that work? Okay, well, what happens there is when we change hello to world within our document, our object type itself, we can always say, let's assign one object to another object, okay? So we're not changing the contents of the prior object that are pointed to by that const pointer. We're changing the object itself to point to something else. Okay.
Right, but it's because my question was, you said if you had in Photoshop you had these giant documents, you just made a change to one little, one pixel or whatever, it would be shared except for that one change, and that's effectively what you're doing here, I take it.
Yes.
But I'm not seeing where the original state is that you get back by doing the. So there really are 2 of those documents, but they're really basically vectors they're actually references to the objects that have been modified. So it's just the real underlying objects that are being changed and have to have storage, and these are just containers that essentially are free, in quotes, free to have lots of. Is that the idea?
Yeah. Yep.
All right, Sean, we got to get you to the airport. Just
Okay.
giving you that warning.
Okay. Great. So
Thank you, Sean.
I guess we're good here.
Incredible talks.